Hello, I'm Pierre Gèlat from the Department of Surgical Biotechnology at UCL. I'm going to discuss with you the involvement of my team in an international software benchmarking exercise applied to ultrasound neurostimulation scenarios. Ultrasonic neurostimulation is a rapidly growing field in which low-intensity ultrasound is delivered to nervous system tissue non-invasively, resulting in transient modulation of neural activity. In contrast with other non-invasive interventions, such as transcranial electric stimulation and transcranial electromagnetic stimulation, ultrasound neurostimulation offers the prospect of highly targeted interventions within the brain. This could potentially translate into clinical applications to treat neurological disorders, including chronic pain, epilepsy, psychiatric disorders, and even neurodegenerative disease by promoting neuronal plasticity and silencing or exciting specific cell types. There has been increasing interest in ultrasonic transcranial stimulation, both within the scientific community and in the popular press, such as this article which appeared in The Guardian in June of last year. Despite this, a set of standardized guidelines and recommendations for all researchers using transcranial focused ultrasound in humans has yet to be agreed upon. A key component to this standardization lies in the validation of computational models simulating the propagation of ultrasound in heterogeneous media. The International Expert Group on Transcranial Ultrasonic Stimulation Safety and Standards, or ITrust, is an international consortium working together towards the safe and effective application of transcranial focused ultrasound for neurostimulation. ITrust aims to establish consensus on expert guidelines and standardization for this neuromodulatory technique. The planning group of ITrust aims to establish recommendations and guidelines for guidance and planning of focused ultrasound for the purpose of neurostimulation, including acoustic and thermal simulations, calculating exposure and dose parameters, and skull imaging. So here's a list of the participants that took part in the benchmarking exercise, and a variety of computational methods were employed across these institutions, all with their respective strengths and limitations. So these methods include the hybrid angular spectrum approach, the case-based pseudospectral method, finite difference time domain methods, the finite element method, and the boundary element method. My team was invited to participate in this transcranial ultrasound simulation benchmarking exercise using our software Optimus. Optimus is an open source general purpose ultrasound simulation platform. It was originally developed for transabdominal ultrasound treatment planning applications, and we have since broadened the range of scenarios which can be tackled. And this includes osteoid osteoma and in utero sound propagation. The boundary element method has the advantage that it can be implemented in the frequency domain, thereby avoiding complications associated with time domain solvers. Furthermore, no volumetric grids are required. Instead, the problems are formulated using a set of closed surfaces representing the different boundaries of each domain. Domain truncation effects are therefore avoided. And the boundary element method has the advantage of having little to no numerical dispersion. However, there is a high implementation effort and involves high RAM consumption. Our recent developments, however, have mostly overcome these issues. Three types of formulations have been implemented in Optimus: the Helmholtz transmission formulation, where distinct subdomains are immersed in an infinite fluid region, a nested formulation with nested domains, and a multi-trace formulation where domains are in contact with one another. So all these three formulations were required to tackle the ITrust benchmarks, and in fact, the multi-trace formulation was developed specifically for this benchmarking exercise. Two acoustic sources were considered in this intercomparison: a bowl-shaped transducer and a piston transducer, both vibrating at a frequency of 500 kilohertz. As part of this talk, I will present 4 of the benchmark cases forwarded to other participating institutions in this first phase of the work. The first benchmark consists of a bone slab immersed in water. The second consists of 5 layers of various brain tissue types. The third benchmark comprises a slab of skull. The fourth consists of a brainstem nested into a cranium. For each benchmark, excitation from both the piston source and the bulb transducer was considered. In each case, the results were compared with K-wave. Whilst it can be challenging to establish a ground truth solution, K-wave includes an axisymmetric option which enables very fine computational grids to be used, which is relevant to a subset of the benchmarks. Results are shown here for the bone slab and a bowl source. And for the same bone slab with a piston source, and we can see good agreements between both methods. The field along the axis of propagation is plotted in the graph displayed, again showing good agreements between both solvers. So similar plots are now shown for the layered media benchmark for a bowl source, and now for the piston source. And the actual pressure magnitudes are again in good agreement. Here are some results on the skull slab immersed in water. Whilst we note good agreement between K-wave and Optimus in the beam plots for the bowl source and the piston source, we can see that the actual plot for the bowl source shows some disagreement in the near field of the source and in the focal region. This is currently under investigation. So results on a full skull and brainstem are shown on this slide for the bulk transducer. And here are some beam plots in the XZ plane showing good agreement. Although I have to say that this job did present some computational challenges, and we had to run this on a cluster node. So in conclusion, we have presented boundary element method calculations using the open source software Optimus applied to solve the propagation of ultrasonic waves inside the cranium with good agreement with the K-wave solver. There nevertheless remains challenges in establishing a ground truth in complex scenarios. So this endeavor was part of a wider software benchmarking exercise, which was recently published in the Journal of the Acoustical Society of America. So feel free to go to our GitHub repository and install Optimus. And if you have any queries, please contact us at the following email address. Thanks. I would like to thank you all for your attention, and I would like to acknowledge the following.